Welcome back. If you remember in our last video we were talking about the probability of a desired event occurring, and the way that we could calculate that was to take the total number or the cardinality of all desired events and divided that by the cardinality or the total number of all events. We called them all possible outcomes. And the way that we learned how to count up the number of desired events and or the number of all possible events was to divide it up into tasks. Some of the tasks that I remember was a 6-character password or how to label the chairs in an auditorium. And a part of that was the product rule and the sum rule. The product rule told us that if we had a series of tasks that were sequential in nature, that it was a logical and. We have to do this and that, such as a license plate number or a password. Each character in the license plate or the password would be tied together through a logical and that product rule said that we would take each one of the tasks and we would multiply them together. The sum rule, on the other hand, was a logical or. The logical or tells us that we can do this or that when I have my task identified. Our example of this was a password that is 6 in length or 7 in length or 8 in length. We said, how many possible passwords could you have if you can have a password that is 6, 7, or 8 in length? That logical or means that I would identify the total number of each one of the individual tasks, and then I would add the tasks together in the sum rule. What I'd really like to do next is to formalize these counting rules that we have been applying. So the first thing that we're going to introduce is a permutation. So the definition of a permutation as a method of counting would be a set of distinct objects that are arranged in an ordered arrangement of these objects. And the key word here is order. So we're going to use permutation as a counting method when order matters. Think of a license plate number. The order of the characters on the license plate matters. Your password, for that matter. The order of the characters in a password matter. 1, 2, 3 is not the same as 3, 2, 1. So when order matters, we're going to think to ourselves permutations. So let's say, for instance, that I have some set A, and I'm going to make it A, B, C, and D. 4 elements in set A. We could say that A, B, and C, once again, these should all be comma separated. This is actually a permutation of S. A permutation of A. So if ABC is a permutation of A, actually it would be a 3 permutation of A because I'm taking 3 of the elements out of my original set A. We could say that B, C, and A is also a permutation of A. But is a different permutation of A because order matters. A, B, and C as a password or a license plate would not be the same thing as B, C, A as a license plate or a password. So I could see that if I just took the letters A and B, that this would be a 2 permutation of the set A. So with all of the other discrete structures that we've talked about in this class, of course there is a notation that we would use. I could say that this is the notation that we're going to use is a permutation of Nr objects. So we have said this is the number of R permutations of a set that contains N elements. It can also be written this way. So with my set A, we started with 4 elements. I could say that we have 4 elements and we were choosing 3 of those elements, or I know that when we were doing A and B, I had 4 elements in set A, and we were choosing just 2 of those. So those are the notations. We could also say, with N and R, I could also say permutations of 4 and 3, or permutations of 4 and 2. This was, I believe, A, B, and C. Since I can't see it on my screen, it looks like this is A and B. The total number of 2 permutations from a set that contains 4 elements. There's another thing that we have to take into consideration about permutations. I said that we are using the permutation method of counting when order matters. Another thing that we have to take into consideration is whether or not I can have repeating elements. Think for just a minute about our license plate. I'm going to say that we have 5 characters in our license plate. Is it perfectly acceptable to have a license plate that is made up all of letter A's, or for that matter, a password? Would this be an acceptable password? Can I repeat the value that I have chosen for a previous character, say for instance A? If I can, the way we decided it, if I set these up as individual tasks, we said that we were going to use our product rule to multiply each one of these individual tasks together, and what we were going to get if we are choosing letters, and there are 26 capital letters, I have 5 of them in my license plate or my password, so I would say 26 raised to the power of 5. If I can have repeating elements, that means that selecting an item out of the pool, for this purpose that means selecting a letter out of my alphabet, does not remove it from the pool of possible options that I could choose. So for each one of the individual 5 characters, I have 26 options that are available to me. So I take this, it's actually going to be n raised to the power of r, where n is the number of elements that I have to choose from, and r is the number of elements that I'm actually going to choose out of that pool. So, n is the number of elements that I have to choose from, the number of elements in the original set, or the number of letters in the alphabet, or the number of characters in my password when a single character can contain uppercase letters, lowercase letters, numbers, and 7 symbols. R is the number of elements that I'm actually going to choose. For this particular example, I'm choosing 5. There are 5 letters in my license plate number. So I'm just going to make sure that I highlight this formula right here is when I am using permutations, when I can have repeating elements. What happens if I can't have repeating elements? What happens if selecting an item out of the pool removes it from the pool and I cannot use it again? What happens if, for instance, I could not have A as a password, that my password manager said you cannot reuse the same element? How is it going to change this formula that we have come up with for permutations when I can have repeating elements? If I cannot have a repeating element, I'm going to just lay out 1, 2, 3, 4, 5 elements again. And let's say that I have a set that contains n elements. It seems like I would have n for this first one, and then n minus 1 for the second one, because I can't repeat the first one, and then n minus 2, n minus 3, n minus 4, and so on and so forth, until I end up with, down here at the bottom, n minus r plus 1. This formula is actually going to generate n factorial divided by n minus r factorial. If I cannot have repeating elements, if selecting an element out of the pool, I call it the pool, removes it from the pool so I can't select it again, it is going to change my equation a little bit, because now I have to remove repeating values. So an example of this where I cannot have repeating elements is every Olympic Games that you have ever watched. There are a pool of people who are competing for the medals. There is 1 gold, 1 bronze, and 1 silver medalist. You cannot have one competitor that wins a bronze and simultaneously wins the gold, because as soon as they win a medal, it takes them out of the running for winning other medals. Okay, I think my analogy is breaking down, because we all know Olympic medal winners win their medals based upon their time or their skill. So I'm going to give you another example that we're going to use. Let's say, for instance, that I have a pool of 100 people, and out of those 100 people, I am going to choose 3 prize winners. The first, the second, and the third prize winners. How many different ways can I select 3 winners out of a pool of 100 to give the prizes to when, if a person is chosen for a prize, say the third place prize, they cannot then win the second place prize. So I'm going to ask myself two questions. The first question is always going to be, does order matter? So let me move that up here and we're going to write, does order matter? If the answer to that question is yes, then I know that I'm dealing with a permutation. And if you said to yourself, no, the order doesn't matter, just ask the first place prize winner whether or not he wants to be first place or third place. So the second question is, can I have repeating elements? Can the third prize winner also win the first prize? For this particular problem, the answer to that is no. We cannot have repeating elements, which means that I am going to use the formula for a permutation with non-repeating elements. Remember, if the answer to this question had been yes, if the answer had been yes, we would just use n raised to the power of r. The number of elements that I have available to me raised to the number of elements that I'm actually selecting if we could have repeating elements like passwords and license plates. But with my prize winners, we cannot have repeating elements, so now I'm going to use the second formula that we are learning, and let's just plug in some numbers. I'm pretty sure that here my n value is the total number of elements that I have to choose from. There is a pool of 100 people that have entered the drawing. My r value is the total number that are being selected. I am selecting 3. First place, second place, and third place, so I am selecting 3. So I'm going to put 100 factorial divided by 100 minus 3 factorial. This is going to give me 100 factorial over 97 factorial. Now, before you break out your calculator and you start plugging away at 100 factorial and blow your calculator out of the water, we're just going to do a little bit of simplification. Because if I remember what factorial means, it means 100 times 99 times 98 times, well, that would be 97 factorial divided by 97 factorial. And I'm pretty sure that I can simplify those two, which means that I end up with 100 times 99 times 98. And if my math does not escape me, this gives me 970,200. So there are 970,000 different ways that I can choose 3 winners out of a pool of 100 people. So let's try this one more time. I'm pretty sure that example above that I used was a 5-character, let's just call it a license plate. And I said this was our license plate. But what happens if I cannot have repeating values? So if we have no repeats and the order in which they are chosen matters, we're just going to go with letters for now. So everything, that means that my n value is going to be all capital letters. That would be 26. Looks like my r value is going to be 5 because I'm choosing 5 of those. So that's going to give me n factorial divided by n minus r factorial. If I plug in my numbers, this is 26 factorial divided by 26 minus 5, and all of that is in factorial. This is 26 factorial divided by 21 factorial. I'm going to move this over here because, again, before I just put in these very, very large factorials into my calculator, I should probably simplify. Factorial, this would be 26 times 25 times 24, 23, 22, and finally 21 factorial, all divided by 21 factorial. If I factor out the two very, very large factorials, this leaves me with a very large number. It looks like 7,893,600,000. So this is going to be a much, much larger number if I can have no repeats. Alright, so I'm going to have you give it a try. Your turn. We're going to go back to that same video store with the same 3 baskets, but this time I'm going to have you draw 3 videos, and when you draw them, you are going to record the videos that are being drawn. If you are keeping track of the order in which they are being drawn, I want you to tell me how many possible samples you can have from pulling 3 videos from just the PG basket. Alright, so I want you to do another your turn. This time I want you to turn to page 96 in your textbook. I'm pretty sure that for the international version that's going to be page 109. And I want you to do number 8. And I also want you to do number 9. For this purposes, I am going to have you assume that no repeats are allowed. And I just want you to practice simplification of factorial expressions. I'm going to give you 2 very, very critical hints. So I'm going to say that hint number 1 is 0 factorial. Hint number 2 is 1 factorial. What do you think 0 factorial is, and what do you think 1 factorial is? Well, if factorial is I take the number and I multiply it by itself in reducing increments all the way down to 1, this is just going to equal 1. But the beautiful magical power of 0. 0 factorial is also 1. So with those hints, I want you to do your turn. So just to clear this up, we are talking about permutations. And permutations are when order matters. But we have 2 subcategories of permutation. The first one is when I can have repeats. If I can have repeats like passwords and license plates, I'm just going to use the formula n raised to the power of r. If I cannot have repeating elements, I'm going to shorthand this as no repeats. Now I'm going to have to remove all of those potentially repeating values. So this is going to be n factorial divided by n minus r factorial, where n is the number of elements to choose from, and r is the number of elements that I'm actually choosing. So we have 2 separate formulas that we can use for permutations. Permutations are when the order that the elements are chosen matters. So we're going to do our confidence for today. I'm going to have you do your confidence on a scale of 1 to 5. What we have picked up is permutations. And then I want you to do with repeats. I'll call it with repeats. And without repeats. On a scale of 1 to 5, how are you feeling about these? So as we finish this up, you might be asking yourself, okay, permutation is when order matters. What happens when order doesn't matter? I know that license plates and passwords order matters, but sometimes it's just nice to be chosen for the team. It only matters the order for which you're chosen for the team when you're in elementary school and you don't want to be the last one picked to play soccer. But the rest of the time you're just happy to be on the team. Are there different formulas that I'm going to use when order does not matter? And the answer is yes. And we're going to learn that next.